condition. Here you see this. So this is the register with synchronous clear and load. So you can see this synchronous clear CLR and the load LD. Okay, so here you can see this input, that D3, D2, D1, D0, output Q3, Q2, Q1, Q0. Okay, so this is the clock CLK. So here, so this shows the simple register which can be loaded and cleared on the rising edge of the clock. So on the rising edge of the clock, that can be represented as this, if CLK event and CLK equal to 1. So similar to your previous one. Okay, so here if CLR equal to 1, the register is cleared, and if LD equal to 1, the inputs are loaded into the register. Okay. So after this, you can see that we are using this if corresponding to that if. Then if CLR equal to 1, then so this will be cleared, means Q, this value will become what? 0, 0, 0, 0. Okay. So here the register is cleared. That means the value of Q will become what? That is Q3 equal to 0, Q2 equal to 0, Q1 equal to 0, and Q0 equal to 0. So that is what? Q will be equal to 0, 0, 0, 0. Okay. And if LD equal to 1, the D inputs are loaded into the register. So that is what we can see. As if LD equal to 1, then Q equal to D. Okay. So this is what happens in this register. So this is how you can model this using BSDL code. So again, this CLK, if there is a rising edge of the clock, then this sequence will be repeated. Okay, so these statements inside the process will be repeated. So that's why this CLK need to be put inside the sensitivity list. Okay. So after writing this, here you can see that there are two if statements. So you have to end all of this. So corresponding to this if, you will write this end if. Corresponding to this if, you will write this end if. And corresponding to the process, you will write this end process. So this is what we saw. So in the BSDL code for the register Q and D, you can see all these are what? Bit vectors. So bit vectors, these are 4 bit vectors. We saw that Q3, Q2, Q1, Q0. Similarly D3, D2, D1, D0. Okay. So dimension is 3 down to 0. Okay. Okay, so as the register outputs can only change on the rising edge of the clock, so that's this is what figure 2.42. Okay. Yes, since the register output can only change on the rising edge of the clock, that is what? CLK. So that's why this CLR is not in the sensitivity list. Okay, so it changes on the rising edge of the clock, so that's why this CLK need to be put inside the sensitivity list. Okay, so CLR is not in the sensitivity list. So after that we are testing the rising edge of, if it is tested after the rising edge of the clock that CLR equal to LD equal to 0. Okay, so then no change, since so that is what this condition already we discussed. Okay, so when if CLR equal to 1, then Q is reset. Else if LD equal to 1, then Q value will be equal to D. So this is what we saw, a simple register with synchronous clear and load. Okay. So these are modeled by using this BSDL code, that when CLR equal to 1, this is reset. Otherwise the value of D is loaded. So else if LD equal to 1, okay, that is the condition we have written, then Q value becomes D. Next, now we'll see, we'll model a left shift register. Like in the previous example, we saw a left shift register. So we'll model a left shift register using a BSDL process. So here the register, this is similar to your previous figure. except that we have added a left shift control input. Okay. So we'll model a left shift register using VHDL process. So here the register in this figure, that is 2.43. Okay. So this you can see, this is similar to your this figure, but here we have added a left shift control input. So here you can see that left shift control input, that is what here we have added LS, that is the left shift control input. Okay. So LD and CLR, so all these are present similar to your previous diagram. This CLK, this is Q3, Q2, Q1, Q0 output, this input D3, D2, D1, 0, D3, D2, D1, D0. Okay. And another input that you can see RIN. Okay. So here we have added a left shift control input, that is LS. So when LS is 1, if LS value equal to 1, then the contents of the register are shifted left. So this is the left shift register. So when it will be shifted, when LS value is 1 and the rightmost bit is set equal to RIN. So these will be shifted, like here you can see, let's say they are saying the value of Q equal to 1101. Okay. So let's wait. So Q value equal to, let's say 1101, and let's say RIN value equal to 0. So when the left shift will occur, so the will be shifted one bit towards left, like 1 will come to this, 1 will come to here, this 0 will come to here, this 1 will come to here. Okay. So that means now this will become 101, this 1 will move away. Now the right side, which is now vacant, so that will be filled with this RIN. That will become what? 1010. So this will happen in this left shift register. So here, that's what we are saying. When LS value is 1, the contents of register are shifted left. So we saw that these are shifted left, and the rightmost bit is set equal to RIN. So the rightmost bit which became vacant, so now that is filled with this RIN. So that is the value 0. So as you saw that the shifting this is accomplished by taking the rightmost 3 bits that we saw, rightmost 3 bits of Q. So that is what Q2, Q1, Q0. As you can see that this is your Q3 most significant bit. This one is Q3. Next, this is Q2. Next, this is Q1, that is 0, and this is Q0, that value is 1. So rightmost 3 bits, that is Q2, Q1 and Q0. So these are shifted. Q3 moves away. Now Q2, Q1, Q0, these are shifted. So now Q0 position, that will be vacant. So that will be filled with this RIN. So that's why here you can see that if you are taking the value of Q equal to 1101 and RIN equal to 0, so now this will become what? Now Q2 down to 0, that is Q2, Q1, Q0 and RIN, means here this is the concatenation. This becomes what? 101, that is concatenated with RIN, that is 0, so this becomes 1010. If you are taking the example, that is Q value is 1101 and RIN equal to 0, so now this will be the output, so 1010. So this value will be loaded back into the Q register on the rising edge of the clock. So if there is a rising edge of the clock, this will occur. So here you see that this is the VHDL code. So here what will be put inside the sensitivity list, that is CLK. On the rising edge of the clock, these statements will be executed. So we then begin and end process. So here we'll first test this condition, rising edge of the clock. If CLK event and CLK equal to 1, then we'll check if CLR equal to 1. Okay, if CLR equal to 1, this will be reset, right? So this is similar to your previous one. If CLR equal to 1, this will be reset. Okay, else if LD equal to 1, then Q equal to D. This is what similar to your previous. Else if LD equal to 1, then Q equal to D. Then another condition we are putting, this is the left shift register, that is if the value of LS is 1. So that is else if LS equal to 1, then Q equal to what? Q 2 down to 0, ampersand are in. So that is the concatenation symbol. Okay. So this is, now you have to end this if and if, you have to end also this outer if, then you have to end this process. So end process. So this is the VHDL code for left shift register with synchronous clear and load. So just we have added this part, that is here we have added this LS left shift register. Okay, again see this RIN we have given as the input. So this statement is added, that we are taking another condition, if LS equal to 1. So now there will be left shift. So these input whatever you have taken Q value, so they will be shifted towards left, and the rightmost bit that will be vacant. So where now the value of RIN will be concatenated. So this will be your output. Okay, so in the next figure we'll see a synchronous counter. Okay, so we'll see a simple synchronous counter. So here also on the rising edge of the clock, the counter is cleared. That is when CLRN equal to 0, and it is incremented when CLRN equal to EN equal to 1. Okay, so here you can see this Q, that is bit vector we are taking, Q3, Q2, Q1, Q0. Okay, this is the counter. Here you can see these are the inputs. EN, here CLRN, CLR its inverter, that is CLRN, then CLK. So here you can see this VHDL code. Now here Q is the internal signal, so that will declare this. So signal Q, that is the unsigned, we are declaring it as unsigned 3 down to 0. Okay, so unsigned vector, that is here 3 down to 0. So you can see that Q3, Q2, Q1, Q0. So this is your means you can see that 3 down to 0 indices are from 3 to 0, that is Q3, Q2, Q1, Q0. Okay. Then here you can define this process. So it occurs on the rising edge of the clock. So CLK need to be put inside the sensitivity list. Then within the begin and end process, we'll check for the rising edge of the clock that if CLK event equal to 1, if CLK event and CLK equal to 1, that is on the rising edge of the clock. If value of CLRN equal to 0, then the counter is cleared. So here in this synchronous counter, the counter is cleared when the value of CLRN equal to 0. So this you have to write using VHDL code. So that will write if CLRN equal to 0, then this will be set to 0. Okay. Then Q equal to 0, 0, 0, 0. Okay, that is the counter is cleared. and it is incremented when CLRN equal to En equal to 1. Okay, so that's what you can model here. Else if En equal to 1. So first you check if this condition is not satisfied. If CLRN is not equal to 0, that means the value of CLRN equal to 1. So that's what, in this condition CLRN is already 1 because this condition is not satisfied. So CLRN equal to 1 and we are checking only for En equal to 1. Then Q will be equal to Q plus 1. So that is what. So it is incremented when CLRN equal to En equal to 1. Here CLRN is already 1 and we are checking the value of En equal to 1. Then this Q will be incremented. That Q value will become what? Q plus 1. Okay. So this is a counter. So its value will be incremented in this condition. So now you have to end this if, inner if, then you have to end this outer if, then you have to end this process. So as you saw that this signal Q, this represents a 4-bit value that is stored in the counter, that is Q3, Q2, Q1, Q0. As in the previous class we have discussed, here addition is not defined for bit vectors. Okay, Q represents the 4-bit value, and this is what as the addition. Here we are doing the addition. Addition is not defined for the 4-bit vectors, so that's why you are declaring this Q to be of type unsigned. Okay. And we can increment this counter by using the overloaded operator plus. We have written Q equal to Q plus 1. So this is defined in this IEEE numeric underscore bit package. Okay. So this statement Q equal to Q plus 1, this increments the counter. So when the counter in the state will be having the value 1 1 1 1, then next increment will set the value what? 0 0 0 0. As you can see, so 1 1 1 1. If you'll add 1, you know this 1 plus 1 0 carry 1, 1 plus 1 0 carry 1, 1 plus 1 0 carry 1, 1 plus 1 0 carry 1. So this 4 bit you can see that 0 0 0 0. So the next increment takes it back to the state 0 0 0 0. That Q3 will become 0, Q2 will become 0, Q1 is 0 and Q0 will also become 0. Okay, so here we saw a simple synchronous counter. Next we'll see VHDL model for a generic counter. So that is 74163, which is a generic counter. In the next figure here you can see. So that is 74163, which is a generic counter. You can see these are the inputs D3, D2, D1, D0, outputs Q3, Q2, Q1, Q0. This CLRN, LDN, PT, all these are the inputs. C out, this is the carry out, and CLK clock is the input. Here, okay, so it is a 4-bit fully synchronous binary counter. So these are available in both TTL and CMOS logic families. Okay, so this represents what? That is the general type of counter. So here, in addition to performing the counting function, it can also be cleared and loaded in parallel. Okay. So all these operations are synchronized by the clock, and all state changes these take place following the rising edge of the clock input. The rising edge of the clock input, That is, we can say what CL will check if CLK event and CLK equal to 1, then those will be those statements will be executed again. So this counter has 4 control input, that is CLRN, LDN, P and T. Okay, you can see that. So CLRN, LDN, T and P. So these are the 4 control inputs. So how this will operate? So this will operate as follows. You can see if CLRN value equal to 0, then all flip-flops are set to 0 following the rising edge of the clock. Now if CLRN equal to 1 and LDN equal to 0, then the D inputs are transferred in parallel to the flip-flops following the rising edge of the clock. And if the value of CLRN equal to LDN equal to 1 and P equal to T equal to 1, then the count is enabled. The counter state will be incremented by 1 following the rising edge of the clock. And if T equal to 1, the counter generates a carry out C out in state 15. So C out will be equal to what? That is Q3, Q2, Q1, Q0, T. Okay. So you can see the truth table of this figure here. So this you can see the summary of operation of the counter. That is here when CLRN equal to 0. Okay, you can see these are the control signals. What is that? Control signals are CLRN, LDN, P, T. And you can see here what will be the next state. Next state can be represented. That is here Q3 its next state, that is Q3 plus, then Q2 its next state is Q2 plus, then Q1 plus, then Q0 plus. So next state can be represented as Q3 plus, Q2 plus, Q1 plus and Q0 plus. So when CLRN equal to 0, all flip-flops are set to 0 following the rising clock edge. So here you can see that when CLRN equal to 0, we do not check for the others. Others are don't care. We are checking what? If CLRN equal to 0. That's why here we have put this don't cares. If CLRN value is 0, then these will be set to 0. That is clear. Then if CLRN equal to 1 and LDN equal to 0, you can see that CLRN value is 1, LDN equal to 0. What is the value of P and T? We don't care. So that is don't care, or we'll put X here or cross. This indicates don't care. So we are checking only for what? Value of CLRN equal to 1 and LDN equal to 0. In this case, D inputs are transferred in parallel to the flip-flops following the rising edge of the clock. So here you can see D inputs are transferred. That is what? Next state, that becomes what? D3, D2, D1, D0. So parallel loop. Okay. Next, if CLRN equal to LDN equal to 1, P equal to T equal to 1. That is this last one you can see. CLRN equal to LDN equal to 1. CLRN is 1, LDN is 1. Okay. And P equal to T equal to 1. P equal to T equal to 1. So the count is enabled. Okay. The count is enabled and the counter state will be incremented by 1. That is present state plus 1. Okay, and here you can see that when CLRN equal to 1, LDN equal to 1, if here PT, this is 0, then next state will be what? Q3, Q2, Q1, Q0. So here the count will be incremented. Yeah. Okay, so here the truth table, this summarizes this. You can note here that CLRN overrides the load and count functions. That is when CLRN equal to 0. So here clearing occurs regardless of the value of LDN, P and T. So we saw that LDN, P and T, these are don't care. So this is now cleared, that is 0, 0, 0, 0. So similarly here LDN overrides the count function. So the CLRN input on this is referred to as synchronous clear input. So now you can see this VHDL description of the counter which is given in this figure. So you can see this VHDL code for the above counter. So this is the 74163 fully synchronous counter. Here, as you know, this double dash line, this is for the comment line. So here we have written what 74163 fully synchronous counter. So here we are using this library, IEEE library. Already we have discussed in the last class. This library I have discussed. Library, this is the keyword. Then you have to write IEEE. So we are using what numeric underscore bit package. So use IEEE.numeric_bit.all. Then entity name is that is C74163. So we have given this name, that is this stands for counter 74163. Then is keyword. Then next you have to declare this port. So in port now you see here what are the input signals is. So all these are the input signals that you can see, that is here LDN, CLRN, P, T and also this CLK. Okay, so these are all input signals. So mode is in, type is bit. Okay, and next is D, this one. Okay, this is also input. This is what, that is unsigned. You can see this, and here the size is what 4, that is D3, D2, D1, D0. Okay, so here D mode is in, type is what unsigned. So 4, that is 3 down to 0. Okay, so D3, D2, D1, D0. Similarly C out, this is the output bit. So mode is out, type is bit. Similarly Q out, this is Q out. So this is what mode is out, this is unsigned. Now size is 4, that is 3 down to 0. Next you have to use this end keyword, then entity name, that is C74163. Next you have to define describe this architecture. So architecture keyword, then architecture name. So here suppose I am giving B74163, then off keyword, then the entity name is 74163, then is keyword. Next you have to declare if any internal signal is there. So internal signal Q. So signal Q, internal signal Q. So that is again, so here internal signal means no mode in or out will not mention, the type will mention, that is unsigned. Size is 4, that is 3 down to 0. So Q is the counter register here. Now within the begin and end, so here we'll describe this architecture. Now here your Q out, this will be equal to what? This depends on Q. Q out equal to Q, this is the internal signal. Q out equal to Q. And C out, carry out, this is equal to what? That is Q3 and Q2 and Q1 and Q0 and T. Okay. Okay, so this will be Q3 and Q2 and Q1 and Q0 and T. Next we'll define this process. So here what should be in the sensitivity list, that is CLK. Then within this begin and end, you have to describe the process. Within this begin and end, you have to describe the process. So here you see that if here there will be rising edge, that is, you can write if CLK event and CLK equal to 1, then here if CLRN equal to 0, as you know, this will be reset. So if CLRN equal to 0, then Q equal to 0, 0, 0, 0. Okay. Else if LDN equal to 0, if LDN equal to 0, then the D inputs are transferred. So here, if LDN, else if LDN equal to 0, then Q equal to D. Okay. You see, this is the outer if, means whenever there is rising edge of the clock, after that only we'll enter inside this, we'll check all these conditions. So on the rising edge of the clock, all these occurs. So on the rising edge of the clock, if CLRN equal to 0, then Q is reset, Q equal to 0, 0, 0, 0. And else if LDN equal to 0, then D value will be assigned to Q, Q equal to D. Then you can see else if P and T. So this is the logical AND we are putting. Else if P and T equal to 1, then Q equal to Q plus 1. Okay. So PT, this is nothing but P and T. Okay. So when P and T, this is equal to 1, this is present state plus 1. This here we have written. Okay. So P equal, yes.
He opened and went.
Hello. Yes, Arpan.
Sorry.
Okay, so here you can see else if P and T equal to 1. You see, if this condition is not satisfied, then what? LDN value becomes 1. So automatically here LDN value is 1 and we are checking for this P and T. Okay, this is the logical AND. If P and T this is equal to 1, then Q equal to Q plus 1. That is the value of Q will be incremented. So that is what you can see here, that if CLRN equal to LDN equal to 1, okay, so that is what CLRN equal to LDN equal to 1. So here first we are checking this condition, CLRN equal to 0. If this is not satisfied, then CLRN value becomes 1. If this is not satisfied, then LDN value becomes 1. Then we are checking that if P and T, these are 1, then Q equal to Q plus 1. So that is what here you can see, that Q equal to Q plus 1. If CLRN equal to LDN equal to 1 and P equal to T equal to 1. So in case of logical AND, as you know, that if both of them are 1, that P and T both of them are 1, then so this will become 1. Otherwise that is 0. So if this condition happens, then here you can see that you have to increment the value by 1. So that is present state plus 1. So here that's what we have written here. Okay. So then you have to end this if, next end this outer if, next end this process, next you have to end this architecture. Architecture name is B74163. Okay. Okay, so now we saw this, that is 74163, which is a generic counter. So here we saw this BSDL description. So as you can see, here the counter output, that is Q out, this changes whenever Q changes. Okay. So here we just saw this code. Now, so here we are using what, since Q is of type unsigned. Okay, so we can use the overloaded plus operator from the IEEE numeric underscore bit package. So that's why we are now using this IEEE numeric underscore bit package. So to add 1 to increment the counter. Okay, so next example we'll see the example in the next figure. So here we are using what? That is cascaded to 74163. So we'll use this 74163 counter to 74163 counter. They will be cascaded to form an 8-bit counter. As we saw in the example, that was a 4-bit counter. So now two 74163 counter will be cascaded to form an 8-bit counter. Okay. So here in this figure you can see, so this is one 74163 counter and this is another 74163 counter, so they are cascaded. Here you can see this is a CLK clock given as the input. So here you can see this first, all these are input. First 74163 counter you can see, that is here CLRN, LDN, this is T1 we are taking, this is P, Q out 1, this is Q3, Q2, Q1, Q0, and similarly D in 1, this is D3, D2, D1, D0. And now this C out, this will be what? This we have taken as carry 1. So here you can see these are the inputs, that is CLRN, LDN, this carry 1 and P. Here you can see that this is the output, that is Q3, Q2, Q1, Q0, which is Q out 2, and this D in 2, you can see D3, D2, D1, D0, and here carry out, C out, that is nothing but carry 2. So here you just see, so when the counter on the right side is in the state 1111, okay, so counter on the right side is in the state 1111 and T1 equal to 1, this T1 equal to 1, carry equal to 1, okay, sorry, carry 1 equal to 1, okay, so this carry 1, so this will be 1, okay. Then for the left counter, PT equal to 1, so this is nothing but P and T, okay. So PT equal to 1 if P equal to 1. So just here. Okay, so here you see this 8-bit counter. And you can see the VHDL model for this 8-bit counter. Like here using this IEEE library. So this is the library keyword. Here library name is IEEE. We are using this numeric underscore bit package. So use IEEE.numeric underscore bit package. Similar to your previous. Here we are using what? You see 8-bit counters we are using, like we have seen what 4-bit adder. So there what we have done, that in 4-bit adder, so we have used 4 full adders. So each of the full adder are one component of that 4-bit adder. So similar to that, here we are using what? Cascaded counters. So where we are using 2 counters, 2 74163 counter. So now each of these will be one component. So you have to describe the component also. First you have to describe at a top level. Okay, so that is the 8-bit counter will describe, like we have earlier described adder 4. Then you have to describe each of the components. So here each of the component, that is here you can see each counter will describe as a component. So first here you see will describe it as a top, will describe at the top level. So that is you have to use this entity keyword. Entity name is 8-bit counter, then is keyword. Then you have to describe the ports. So here you can see that port keyword. Now what are the inputs and what are the outputs? So here you can see that this CLRN, LDN, okay, P, then T1. If you are considering this 8-bit counter, so total you consider this as a whole. So here what are the inputs like CLRN, LDN, P, and this T1, okay. So this T1 will be input and this CLK, okay. So CLK is the input. So all these are of type what? Bit. So mode is in, type is bit. You can see D in 1 and D in 2, okay. So all these are what? You can see here also these are input signals. So mode is in and type is unsigned. Unsigned, size is 4, 3 down to 0. Then count, this will be what? This is the counter, okay. So this is the counter. So this count, this will be what? Mode will be out. This will calculate and find out. This will be the output. Mode is integer. And what will be the range here? You can see that this is what? 8 bits, 4 plus 4, 8 bits. So 8 bit means 2 to the power 8, that is 256. So range will be what? 0 to 255. So here 8-bit counter. So this will be having the value, that range will be from 0 to 255. As 2 to the power 8, that is 256. So range will be what? That is from 0 to 255. So this range is a keyword. So you are describing. And what is the range? You will mention here, that is 0 to 255. And carried to. So this you can see, this is the output bit. So carried to, mode is out, type is bit. Then you have to use this AND keyword. Then the entity name, that is 8-bit underscore 8 underscore bit underscore counter. This is the entity name. Then you have to describe the architecture. So architecture name we are giving cascaded underscore counter. Then you have to use this off keyword. Then the entity name is 8 underscore bit underscore counter. So this is the entity name. Then is keyword. So next you have to describe the component. So you can see this is the component keyword you have to use. Then component name is C74163. Then you need to describe the port. So port, what are the input and output signals over here? That is input signals LDN, CLRN, P, T, CLK. Okay. So individually we are considering each component. So here you can see we have written T, not T1. So P, T, CLK. All these are what? Input signals. Mode is in, type is bit. Similarly, next this D, individual component we are considering. Just write over D here. Okay. For 8-bit counter, this is D in 1, D in 2 is there for each component. So here we will write this D. Mode is in, type is unsigned. This is 3 down to 0. And another is C out. Here mode is out, type is bit. For each individual counter there will be a C out. Okay, so that is carry out. So mode is out, type is bit. And another is Q out. So where the mode is out, type is unsigned, 3 down to 0. Then you have to write this AND component. These keywords you have to write. So AND keyword, then component keyword. So this is the description of each component. So next, whatever the internal signals are there, so those you need to describe. So internal signals, you can see this carry 1. This is the internal signal. So in between these two counters, you can see this is the internal signal, that is carry 1. Okay. So that I'll write the signal keyword. Signal name is carry 1. as you know, this is the internal signal, so mode will not be in or out. This is the internal signal, and you need to mention that type is bit. Then signal Q out 1 and Q out 2. These are the internal signals. Q out 1 and Q out 2. These are the internal signals. So write the signal keyword Q out 1 and Q out 2. So all these are internal signals. So you can see that mode we have not mentioned. This is not in or out. Then type is on 3 down to 0. That is size is 4. Then this architecture within begin and end, you have to describe this. Already you have discussed in 4-bit adder. So you have to mention the level. That is here CT1, CT2. Like there we have mentioned full adder FA0, FA1, FA2, FA3. Here similarly this is counter 1 CT1, counter 2 CT2. Okay. Then column. So here you write each component name. That is here we have taken C74163. Right. The component name is C74163. Then you have to use the port map keyword. Okay. Then here you have to write the signal list. So here for the first you can see CT1. So these are the input signals like LDN, CLRN, P. Okay. T1, CLK, D in 1. And okay, all the input and output signals you need to specify. These are the list of signals: LDN, CLRN, P, T1, CLK, D in 1, carry 1, and Q out 1. So that is what you can see here. Okay, that is CLRN, LDN, this T1, P. Okay. Then this CLK. Here CLK. Then D in 1, carry 1, Q out 1. Okay. So D in 1, carry 1, this will be the output, C out, and then Q out 1. So this one. Similarly for this one, second one, that is CT2. So here again level is CT2. Then here you have to write the component name, again same C74163, which is same as this. Already you have described the component name, which is same here, C74163. So here C74163, then the port map keyword, then write the list of signals. So here for CT2, so here these are the list of signals: LDN, CLRN, P, carry 1. So LDN, CLRN, P, then carry 1. Then CLK, D in 2. Okay, you can see here CLK. Then this D in 2. Then carry 2, Q out 2. Okay. So carry 2 and Q out 2. Okay. So you can see these are the list of signals. And how we'll find out this count? You know, whatever will obtain this Q out 2, and that will be concatenated with Q out 1. Okay. So this is the concatenation symbol. So this will be concatenated and we'll convert that into integer. Okay. So we'll convert that into integer. So as you know, this is 8-bit. So integer range will be 0 to 255. So we'll get one of these values from 0 to 255. So how to convert? You have to use to_integer function. So which will convert that into integer. Okay. Like in the previous class, we have discussed this to_integer function. So to_integer within parenthesis, whatever you are giving. So this converts an unsigned vector A to an integer. So this is the unsigned vector which will be converted into integer. Next you have to write this end keyword, then you have to write the architecture name, that is cascaded underscore counter. Okay, so here we saw this cascaded counters. It's a VHDL code. Okay, so here this function to underscore integer, this converts an unsigned vector to an integer. Okay, so next we'll see, we'll synthesize the VHDL code for a left shift register, which is given in the figure below. Okay. So this is the synthesis of VHDL code for a for left shift register, which we saw from the figure 2.43. Here you can see. Okay, so this one, figure 2.43, which is the left shift register with synchronous clear and load. Okay, so before we do the synthesis, we need to specify what are the target device, like earlier we discussed. So what can be the target device? Like this may be a particular FPGA or CPLD, that is complex PLD, programmable logic devices, so that the synthesizer knows what components are available. Okay, it should know the target device. Okay. So let us assume that the target is a CPLD or a FPGA. That FPGA stands for Field Programmable Gate Array. So here either it is CPLD or FPGA which has got D flip-flops with clock enables. So you can see DC, D stands for this D flip-flop, C, this stands for clock enabled. So clock enabled D flip-flops. So this CPLD or FPGA are having this clock enabled D flip-flops. These Q and D, this Q and D, all these are what? 4-bit vectors. So here updates to Q, when it will be done, this follows this, that you know, on the rising edge of the clock, that is CLK event and CLK equal to 1 then. Okay. So this infers that Q must be a register composed of 4 flip-flops. So which will label Q3, Q2, Q1 and Q0. So here, since flip-flops can change the state when what, that is CLR, LD or LS is 1. So when it can change the state, that is when CLR, LD or LS is 1, at that time it can change the state. So for that we'll connect this clock which enables to an OR gate whose output is CLR plus LD plus LS. Yes, so here you can see this CLR, LD, LS. So when these will be 1, that is either CLR or LD or LS. Okay, so you can use this logical OR. So if one of them is 1, okay, so when CLR, LD or LS is 1, okay, so then flip-flop can change the state. So here for that you can use this logical OR, that you can use this OR gate. So when CLR or LD or LS equal to 1, so that will change the state. So at that time we'll connect the gates to the D inputs. So you can see, so we are connecting the gates to the D inputs. So this is the D input. So we are connecting the gate to the D inputs. Then we connect the gates to the D inputs to select the data to be loaded into the D flip-flops. So here, if CLR equal to 0 and LD equal to 1, D is loaded into the register on rising clock edge. So it's here, CLR equal to 0 and LD equal to 1. Okay. So you know what you need to do when CLR is 0. You know that those mean terms you have studied. So there, when this CLR equal to 0, you have to make it as 1 in the mean term. That you have to take what? CLR prime. Okay. So here you can see we are taking this CLR prime. LD value is already 1. So you just take this LD. So this D is loaded into the register. So here you are taking this D3. Here you can see that CLR prime LD D3. Okay. So you just see here, apart out of these 4 flip-flops, we have just taken the first 2 flip-flops and it has described it. Okay, like here you can see that again this CLR prime, CLR value is what? 0, so you have to take this CLR prime. LD value is 1, so you have to directly take this LD and D. So here, like you can see D2. So if CLR equal to 0 and LD equal to 1, D is loaded into the register. So that's why in the mean term you have to make it as 1. So as CLR equal to 0, you have to take CLR prime. LD equal to 1, so directly take the LD and directly take the value of D. So here for Q3, this is D3 for, okay, you can see that, you can see here, like here CLR prime, LD D3, then here for Q2, this is D2, CLR prime, LD D2, for Q3, CLR prime, LD D3, okay. So that is the first case. You can see this happens on the rising edge of the clock. Another case is what? If CLR equal to LD equal to 0 and LS equal to 1, okay, then Q2 is loaded into Q3. So LS equal to 1, that is left shift, okay. So if CLR equal to LD equal to 0, so in the mean term you need to make it all as 1. So as CLR equal to 0, you have to make CLR prime, LD equal to 0, you have to make LD prime. Okay, so here you can see CLR prime, LD prime, and the value of LS is already 1, directly take LS. Then Q2, okay, Q2 is loaded into Q3. So as this is left shift, here Q2 is loaded into Q3. In case of left shift, you know that here Q3 value will become what? Q2. Q2 value will become what? Q1. So here Q2 will be loaded into Q3. So for this case, that is what? CLR equal to LD equal to 0 and LS equal to 1. So in the mean term, all these you have to make it as 1. So CLR equal to 0, you make it CLR prime. LD equal to 0, you make it LD prime. LS equal to 1, directly write LS. So here also CLR prime, LD prime, LS, and Q2 will be loaded into Q3. So this Q2 is loaded into Q3 and Q1 is loaded into Q2. Okay, as this is left shift. When this left shift happens, when the value of LS equal to 1. Okay. So here when LS equal to 1, so this happens. So either this case or this case, either this or this. So you need to take one OR gate. So you are taking one OR gate here, one OR gate here. Okay. So this figure, this shows the logic circuit for the first 2 flip-flops. Similarly, you can take other flip-flops. So it has been taken for the first 2 flip-flops. So if CLR equal to 1, the D flip D flip-flop inputs are 0 and the register is clear. Okay, so your VHDL synthesizer, this cannot synthesize the delays if there are delays, like when these clauses will be there, clauses of the form after time expression means there are some delays. So this will be ignored by most of the synthesizers. But some synthesizers require that after clauses to be removed. Okay, so this we need to remove. So although initial values for signals may be specified in the port and the signal declarations, usually these are specified. Okay, so here these initial values are also ignored by the synthesizer. These initial values are ignored by the synthesizer. So a reset signal, this should be provided if hardware must be set to a specific initial state. Otherwise, this initial state of the hardware, this may be unknown and the hardware may malfunction. So here, when an integer signal is synthesized, the integer is represented in hardware by its binary equivalent. So here you can see if the range of an integer is not specified, if we will not specify the range of integer, so synthesizer will assume that is the maximum number of bits. Here the maximum number of bits is usually 32 bits. So suppose you are writing what signal, this is the signal keyword, then signal name, suppose you are writing count. Here after that you can see that here in case of these internal signals, so you are not specifying the mode. Here the type, let's say you are taking integer, and the range, suppose you are specifying range is 0 to 7. So if you are taking range is 0 to 7, so how much bit counter will need? That is 0 to 7, that is 8 bits, means here 0 to 7 means total 8. So we can take a 3-bit counter. As you know that if it is 3-bit counter, so 2 to the power 3, that is the range 0 to 7 or total as the size is 8, we can specify by using a 3-bit counter. So 2 to the power 3, that is 8. So if you will not specify this, in the next example, you can see here we have not specified, then this will result in a 32-bit counter. If you are not specifying, so it will take the maximum number of bits, that is usually 32 bits. Okay, so these VHDL signals, they retain their current values until they are changed. So this can result in creation of unwanted latches when the code is synthesized. For example, in a combinational process, if the here you can see this statement, if x equal to 1 and if x equal to 1, then b equal to 1. So this is the end of the statement. Then we have written this end if. This is the end of this if. So if x equal to 1, then b equal to 1. So the condition we have put x equal to 1, then this is the signal assignment operator that we are setting the value of b equal to 1. So here, so this will create latches to hold the value of b when x changes to 0. So we have taken the value of, when the value of x equal to 1, then the value of b becomes 1. So this will also create the latches to hold the value of b when x is changed to 0. Okay. So but that is not required. So to avoid creation of this unwanted latches in a combinational process, we can use the else clause. Here we have not used the else clause, simply we have used this if. So to avoid the creation of unwanted latches, you can use the else clause in every if statement. Like here you can write if x equal to 1, then b equal to 1, else b equal to 0. So this will, if you are writing this else clause, so it will not create the unwanted latches. Like here we have not specified what will happen in case of value of, sorry, here we have specified what, only the if clause, that is what, x equal to 1 when the value of b equal to 1. Okay, we have not specified the else clause. So when the value of x becomes 0, so it will create unwanted latch. That's why to avoid that you can use the else clause. So with, if you are using that, here if you write this statement, if x equal to 1 then b equal to 1 else b equal to 0, means what, when the value of x equal to 0 b becomes 0. So then end of b, end of if. Okay, so for this if, write this end if. So here it will not create unwanted latches. So this will create a multiplexer to switch the value of b from 1 to 0. So it will not result in unwanted latch. So to avoid this, you can use this else clause. Okay, this 2.14 is finished. Is there any doubt? Okay, that study is about chapter 2 as per your lesson plan. So this is up to 2.14. Stop saying. Okay, so mark your attendance. Tell me your registration number. Vaibhav Singh.
Yes, sir. Vaibhav 20410 22001.
Next, Kitty.
Yes, sir. 20410181112.
Next, Varun Pasupalak. Then Supriti.
Yes, sir. 204-101-9297.
And next, Arpan.
Sir, 204-100-203.
204-100.
Yes, sir. 2032.
2035. 35. Okay, next, Subham Patnaik.
Yes, sir. 20410-16177.
Then Saket Kumar.
Yes, sir. 204-101-0003.
Okay, next, Siddhant Swarup Malik. Next, okay, next who are left? Just tell me your.
Sir, Animesh Abhinandan.
Okay, tell.
2041.
Yes.
2041-001.
Yes.
075.
Next.
Sir,
Sir,
Ananya Anindita,
Okay, tell.
204
Yes.
101
Yes.
9341.
Yes. Who else are left? Yes.
Sir, Shweta Padma Das. 204 100 4040.
Sir, Arun Sahu, 204 101 9049.
204 101.
9049.
Next, who else are left?
Sir, Abhilasha Panda,
Yes.
204 101 6027.
Anyone left? Okay, thank you all of you.